thing. So the way to do this is to put this in front and multiply it by the power, which is one smaller. I also want to tell that I saw the grades we have so far on the quizzes, and they make me feel very good. I'm glad that you are doing just pretty much perfect on these little exams, and that's the way to go. So I'm glad that you are doing good, and I hope that be the same thing by the end of semester, because I don't mind. I really would like you to get a perfect grades on this class. Let me try one exercise to use this formula. I'm going to write the solution for problem number 21. In this exercise, I need to prepare powers such a way as first term is going to look like t to the power of -1. Next will be t raised to the power of -2, right? Because t squared is on the bottom. And what's with the last one? Well, square root t is t to the power of 1/2, right? So I'm going to write this as a negative power of 1/2 because it's in denominator, like that. And we know that whether it's t or x or some other variable, it doesn't matter. We use the formula above. So -1 will be multiplied by t, which is raised to the power of -1. You subtract another 1. So this becomes t to the power of -2, right? Plus -2 will be multiplied by, and now the power of t is also going to be decreased by 1. So when I subtract 1 from -2, this will be -3. So in this class, we're going to do lots of subtractions of number 1, and then a little later, we're going to do additions of number 1. So this arithmetic is what we should start to feel good. And finally, the -1/2, the power will be now multiplied by t, which is raised to the power of -1/2 subtract 1. So people like to put it as a -3/2 sometimes, so any way you like, or sometimes people say it's a -1.5, the same thing. Whichever way, again, you put this down is fine, as long as it's correct. So t squared is in denominator with a minus in front. Next, I'm going to have a -2, which is divided by negative, actually power of 3 in denominator, right? Because of negative, so it goes down. Now we have a positive 1 is on the top and 2 goes down, and the power of t that I can write as 3/2, for example, just like that. So we use same exact formula, and the only place to watch out is powers. So we subtract 1 from those, and you can use calculator if you don't feel comfortable subtracting 1. Well, let calculator subtract that number 1 for you, and that's about it. So in these exercises, notice that I was always trying to find derivatives of single pieces. In the next section, they actually give us problems where we have multiplications and divisions. And for those, we have formulas that are not as short. They actually long. And that's why I would be trying to never use these formulas unless I absolutely have to. So I can try exercise like number 1 and show you how this could be done using the formula, and then how this could be done shorter. So in this exercise, we have a product of two parentheses that I need to find the derivative of. So in this parentheses, turns out I could find derivatives on their own by using the fact that this is a product of two functions. One is f and the other is g. And the derivative of this product is going to be f prime times g plus g prime times f. That's what they talking about in this section. So it turns out if you found derivative of function f, which is going to be just number 2, right? Remember, if you take derivative of x itself, it's 1. So if that's 2x, that is 2 times 1. And then if I also find derivative of function g, analogously, it's going to be 3. And then when I substitute these into the formula below, so instead of f prime, I put 2, and that's g prime times f. I should be careful. F prime g plus g prime f, that's the formula. So multiplied by g, which is this 3x minus 2 in the parentheses, plus now g prime, so it's 3 multiplied by f, and f is our first parentheses, which is 2x plus 1. Well, it turns out that usually people like to distribute to simplify this like that. So we're going to have a 6 minus 4 when I distribute 2, and then also 6x, and then plus 3. So we end up with 12 times x minus 1 for derivative. So the reason I don't like this method is because we could first simplify this function. We could distribute, so this will be 3 times 2, which is 6x squared. Then when you distribute inside and the outside products, always give us so-called like terms, which means that we get a 3x here minus 4x, which is negative x. And finally, 1 times negative 2 is minus 2. I say, Alex, what are you doing? I'm doing the exact same exercise, but differently. First of all, I simplified, and now I'm going to produce exact same answer, but I will take derivative of my first term, which is 6 times 2, 12x, isn't it? And then derivative of negative x, since derivative of x is 1, then negative x will be negative 1. So I think it's much faster, and the answer you produce is nice and compact if you need to deal with this answer in the further exercises, then definitely this will be the way to go. But turns out that sometimes you just can't get the answer in such a nice form because you can't simplify your function. And then you have no choice but to use this formula for derivative of product, which is, I guess, supposed to be somewhere. Let me write it here again. And then there is a formula called derivative of a quotient. It's close friend that we're also gonna utilize. So if we have two functions, both depend on x, and if you wanna find its derivative, then we get a f prime times g multiplied and then plus g prime times f. In fact, I just checked and we saw that this formula worked when we found derivative using it, and then we just saw that same thing when we differentiated it directly. That supports the fact that formula works. Also, there is a formula for so-called derivative of a quotient. When you divide, you produce a quotient, a fraction. And on the top of it, it's very similar expression. It's also f prime g and g prime f, but with a negative sign in between, minus. And in denominator, there is a square of g. So usually the second formula is what people have to utilize in problems, let's say like exercise number 13. You just don't have a choice. So I guess I'm going to do it, and we're going to utilize it. And again, I'd like to reiterate, I already said today that I saw grades. I looked at how you're doing in this class so far, and I really like that. So pretty much everyone has a perfect grade, and I really like you to have it by the end of semester, and I will do my best to help. And I think you are doing just great with those quizzes. We're going to have a little midterm exam in a couple of weeks, which I will discuss in very detail next week. I will send you practice, so you will know what's for it, and you will be able to take it home. And I'm not going to supervise you. And this way, I think that usually students get very good results. So we'll see that. We'll discuss this next week. So far, I'm just keep working on chapter 2, finding more of those derivatives. So what I try, let me put one single derivative for this whole thing. So what I'm going to do is I'm going to find the derivative of so-called quotient of these two functions by utilizing the formula for this derivative. So I'm going to treat numerator as function f and denominator as function g. So what I need is to set the structure. I need to find what is f prime and what is g prime separately. And then we'll produce this fraction, and that'll be our answer. So derivative of numerator will be 2x, right? Derivative of x squared, 2 goes on the ground, and minus 3, because derivative of x is 1. And of course, that constant number 2 gives us 0 when you differentiate. Denominator, I have to multiply the power of 2 by that 2 in front, so this be 4 with x, and also plus 5. So now I'm going to need to produce this fraction. So in this fraction, I can put denominator squared. So this whole thing, whatever we have in the parentheses, 2x squared plus 5x and minus 1, and I will square this like that. And then I need to set this f prime g. So f prime is this 2x minus 3 that I will time by function g, which is my denominator. So that same denominator, I'm going to copy just the way it is. It is very tedious, I know. I usually don't ask my students on the tests this kind of exercises, but you might encounter it if you do homework, if you decide to do problems on your own selections. Even though I don't ask you to do this, I just ask you to do problems that are same with what we've done in class, but you can do any problem you like, and you will see some of those using so-called derivative of quotient. So now I'm getting this g prime multiplied by f. So just copied derivative of g, and now I need to multiply it by what's on the top here, by that x squared and so forth. I don't think that they expect you to distribute and to simplify this simply because I guess it just goes nowhere. You just ended up with some nasty looking fraction, and that's your answer. And that's why I'm trying not to mess with this kind of exercises. Again, unless I have no choice. Sometimes there is no choice, and that happens sometimes. We'll see it in the next chapter. So my goal here is to introduce you with these two formulas today and to let you know that you should not use them, these formulas. So you should try to avoid their use. And if you look at the next pages, you're going to see some more exercises here. So I'd like to do one, maybe problem 21, that wants to find the equation of the line. So that's going to be a little extra. So for exercise 21, first of all, I'm going to simplify that function because nobody really needs a product of two parentheses. We already know that, right? So what I'm going to do is I'm going to multiply outside terms, x terms, that will give me 15, 3 times 5, right, with x squared. Then like terms here will be multiplying 3x by -1 and 5x by +4. So we're going to have 20x and minus 3x, which is 17x, right? So just multiply those. 3 by 1 is -3 and 4 by 5, which is 20. And finally, there are two numbers, -1 and +4, so their product will be -4. So once I have this function, then I take its derivative, and that's our favorite part, right? 15 times 2 is 30 with x and then plus 17x. So at this stage, now I'm going to start to use this point, which is 0. In other words, they want me to plug 0 into that derivative. And I want to be a little bit careful because it's a 17, not 17x, right? Find derivative of 17x. X disappears, right? So I'm going to replace letter x with a 0 like that and just get number 17. So 17 is going to be slope. Derivative is always a slope of tangent line to this parabola. So that's a slope. So what's happening here is we got some kind of parabola. We have a point 0, and then we need to find the equation of line that touches it, tangent line. An equation of tangent line is here. Y minus y1 is equal to slope times x minus x1. We already saw it a while ago. So some exercises in these sections, they like these tangent lines, and I already have a slope, and that's great. So I know that I can replace slope with a 17. And I also need to know the point, because now I need to know x1 and y1. And it turns out that point I will pull out from this equation. So I'm going to be replacing my letter x with a 0. So we're going to plug it in and get y out. I say, why would you do all that? Well, that's historically very popular because that's actual use of derivatives. Why we need it? So we can find this so-called tangent lines. So I found the following. When x is 0, y is 4. X, y, we can call it x1, y1. When you say why they call it x0, it doesn't matter, 0, 1. In the formula, they have this numbers 1. So I'm going to go with y minus 4 here. Is of y1, I put 4. And also x minus 0. Okay. So let's see what we get. 17x is on the right side. And I can take that 4, bring it over to the right side as well, and we get the answer. So I add 4, right? And we get the answer for this exercise. Equation of that line, this will be y is equal to 17x plus 4. So some problems end like that, and if you took intermediate algebra, I'm sure you saw lots of exercises that expected you to use this formula. And that's why I think this is something that should be familiar, at least to some people in class, should be familiar, because you get this line equation. And now we're going one step farther. We find derivative which is equal to slope. So that's why probably some people might feel comfortable. But again, these problems are lengthy, and that's why I guess I'm not really much into them. I'd rather take a look at the problems like exercise number 9, for example. No, not 9, 10. Exercise number 10. I think this is a great exercise that actually shows us another way of finding derivatives. It actually opens the door for us into the next section, but next section we'll see next time. So it turns out that my function I can write with power of -1, and that's the idea. And in exercise, we had oh, you said that I didn't do it correctly. Thank you for telling me that. So I just made a mistake, right? So that's great that you saw this, but I will fix it, of course, real quick. So there was a minus, right? Minus. And for some reason, I didn't write minus. I wrote plus. So what you can do, you can fix it. You can put minus where it's supposed to be. So where is minus going? Well, it has to be here, right? It has to be here. So it's actually going to be +4, right? And that's the thing. So you could just notice that this is not a -4 because there's another minus. So it's y +4, right? And then on the other side, we're going to bring this as -4. So it would be minus. So you just change plus with minus basically everywhere. That's very simple. So I'm sure you can do it, but of course you want to be careful, more careful than I, or people say you want to be concentrated, Alex, concentrate. Yeah, that way I guess I'm not going to make, again, mistake. But anyways, thank you so much for noticing. So I have to take a derivative of this function, and turns out I will utilize my favorite only formula for power rule of derivatives, so that -1, the power will go down on the ground, and the power will decrease by 1, so it'll be -1, and then you subtract another 1, so it's -2. So my parentheses will look like same x -2, but now power is negative. And I can write this as a x -2 squared in denominator, right? Because -1 is -2, but I bring it down, so it's positive. And minus sign will give the whole thing negative as a result. So notice that this is the neat way of finding derivative instead of using the formula that I was just introduced with these quotient stuff, right? Because I was able to rewrite my function just as a power instead of being a fraction. And sometimes you can do this, and that's actually called chain rule. So the way we go about this is we utilize a special rule called chain rule. So I'd like to do another exercise here, number 17, to give, well, I guess more positive feelings to you towards the process. So I'm going to be able to do this problem actually 2 ways. One way, I could just simplify this expression and then take a derivative, but then just to support the fact that chain rule is good, I will utilize it again. So in exercise 17, that says take 2 plus 5x in the parentheses and then squared the whole thing. So if they want me to find its derivative, so if I take a derivative prime like that, the 2 will go on the ground, right? And the power will be 1 because we have to subtract from 2, 1, that power rule for derivatives, right? We'll always subtract 1. So that parentheses with 2 plus 5x now is going to be raised to the power of 1. And we found derivative, and that power means nothing, so I could just distribute 2 and say it's a 4 plus 2 times 5, 10, right? Should be careful. Concentrate, Alex. So plus 10x. So this way we got the answer. Or I could actually write this as a product of 2 parentheses. 2 plus 5x times another 2 plus 5x, right? We should put x here. So we could simplify that first. And this is the point that is, I guess, good to notice, that you could distribute this. So if you multiply 2 by 2, you get 4. There are like terms such as a 10x, another 10x, so that'd be 10 and 10, 20, right? 20x. And finally, if I multiplied 5x by 5x, this would be 25 times x squared, right? So this is how I could start. And then what? Well, it turns out when I take derivative of that, that's not going to be the same thing with what I produced. Well, I'm going to tell you, I made that little misprint on purpose to show you what needs to be done on the next step. So if I take derivative of constant 4, it disappears. Then we have 20, right? Because x disappears. Plus 2 times 25 is 50, and then x raised to the power of 5. So please notice this needs to be timed by 5, which is exactly derivative of this parentheses. Derivative of 2 plus 5x is 5, so I had to have 5 derivative of this parentheses multiplied. And that's called chain rule. So you take a outside function squared, and then you subtract 1 and you get 1. But then you take what's inside that 2 plus 5x and take its derivative. That gives you 5. And then when you times it all by 5, you will get correct answer. 4 times 5 is 20 plus 10 times 5 is 50 times x, and that's exactly what is supposed to be. And that's why it's called chain rule. So I want to do number 18, and maybe that'd be good enough for you for today, because I don't want to turn this into a very tedious class meeting, because doing these little exercises, they know, kind of annoying, like too much algebra. So I'm going to do just one more, and then I'll stop and let you go. So chain rule is here. And that's what actually next section is called, how, and we're going to discuss it on Wednesday. So 2 goes on the ground, and the power of my parentheses is now 1. But I have to now multiply it by derivative of inside, just like with that 5, remember? So how to take derivative of what's inside? Well, let me first prepare what's inside, write this as powers. And then when I take derivative of what's inside, I'm going to get 1 derivative of x. Minus 1 goes on the ground, and x will be raised to the power of minus 1, subtract another 1, which is a negative 2. And of course, here's the parentheses that must be preserved, x plus 1 over x. So I just have to copy it the way it is after I took care of that square. And this is my answer. And of course, some people may not like it, so they feel like simplifying this. Well, I would say there is not much you can do. You could technically just leave it like that, but still you could write it a little nicer. So you can put a parentheses with a -1 on the top and x squared on the bottom, like that. So this way we got the answer. So it's called a chain rule. Well, that's actually what next section is called, and I can show it to you. But I guess I don't want to continue because it'd be too much for today. So this chain rule is what I will definitely work a lot with. In fact, that's probably the most popular procedure in calculus when you find derivatives using this multiplying by the next function by what's in the parentheses and so forth. So that's what we're going to need to get used to. And we will be getting used to it next time. So for Wednesday, I guess I'll leave you again without a quiz. I will give you one on Wednesday. Okay. As I said, I was pretty happy with class performance up today, and I hope you will keep it up this way. And sometimes people send me their quiz a little later, and I give full credit for that. So if you ever feel like doing some calculus, and you can always send me your work. If you say miss a lecture or something, you can send it to me later. I will accept it for full credit. Definitely. That's why I keep saying my students, just send me your work whenever you're done over weekend. Or if you just want to get a few extra credit points, just make sure you let me know what this is for, and I will gladly accept it, of course. So I'm gonna stop today, and we'll go without a quiz because I think the problems we've done today, well, you need to look at them a little bit more because they're rather tedious.